in the construction of projection operators I just developed for you, things look very beautiful. You have a matrix, compute its eigenvalues, and you decompose spaces in irreducible spaces, blocks, in simplest case, one-dimensional ones pointing around orthogonals, and any matrix function of the matrix you use to use this intrinsic coordinate for the system becomes just the sum of functions, ordinary functions of a single variable, each one of them evaluated on a separate subspace. It's a nice story, but it's sometimes wrong. It's kind of correct in many cases that physicists encounter with quantum mechanical and classical mechanical settings, but in general, it's not true, and it's a simple fact of algebra that you can only learn by going to slightly more abstract thing than previous example. Instead of using matrix entries 1, 2, 3, 4, we'll just look at a general 2x2 matrix, and it'll turn out there is a chance, a decent, 50-50 chance in some sense, that we cannot diagonalize that matrix, and there is more information on it just than the eigenvalues. That's called Jordan form, and let me quickly explain it. Consider a 2x2 matrix which has 4 arbitrary entries, real, maybe complex numbers. So the characteristic equation is determinant of m minus lambda I. You expand it as a polynomial in lambda. And you notice that if lambda was 0, that will be just determinant of m. So that fixes this term. There is always a term which is just L squared, doesn't care about the matrix. And then the one that's linear, you look at it and you realize that's just a trace of the matrix. That's a very general result in arbitrary dimension, where you find out that characteristic equation can always be written as polynomial in parameter lambda, the one that you use to find roots or eigenvalues. And the coefficients are traces of powers of the matrix. A very useful observation. It's useful because all of those quantities are invariant under a very large group of transformation called similarity transformations. So they're somehow invariant quantity of a matrix, even when you write it in very specific coordinates like M11, M22, M21, M12. This is just quadratic equation, and every one of us remembers how to write quadratic equation, especially when the coefficient of the first term is 1. So you get the second term, 1/2 of it, happens to be the trace. Then you square it and subtract 4 times the first time. This is 1, etc. These are the roots. We are done. In general, lambda 1 not equals lambda 2. That's what we have done in the preceding lectures. We have done with that case where the 2 eigenvalues are the same. That happens in the case if this discriminant vanishes. The matrix can either be brought to diagonal form. Everything we've done so far works, no problem. But then we have a pesky case. It cannot be brought to diagonal form. In this case, one can show that Jordan, I say Jordan because he's German, not Jordan, not a basketball player, but a German physicist, mathematician. It's a piece of, boring algebra I don't want to subject you to, but the main thing is that diagonalize, then one can show that it can always be brought to diagonal form plus once above the diagonal, and this is the simplest case. Because this matrix has a form of upper triangular, meaning something on diagonal, something above it, it's very easy to guess what the first eigenvector is. It's just 1, 0. Obviously, when you multiply it, you just get lambda times 1, 0. But what about second eigenvector? Well, there is no second eigenvector. The best we can do is we can just write other direction in two-dimensional space. Just choose it to be orthogonal. Just to span the space, we have that m minus lambda, a unity, applied twice is 0. Easy to check for you because applying it one just erases the whole thing. But it's not an eigenvector because if I multiply it by the thing that I use to construct projection operators, so this is for the first eigenvalue, remember that should give me the second eigenvector. If I do that, I get lambda times eigenvector, but then I get also an upper component, 1, and I multiply it by 0. I just pick up 1, which is actually the second eigenvector, the original guy. So this is not an eigenvector because if I bang it by my usual block that I use to construct the projection operator, I get a mixture of this thing with the first eigenvector. That's obviously not normal. So there is actually only one eigenvector, and then there is this, straggler. If you compute matrix M to mth power, then what you get in upper triangular matrices, what's on diagonal gets raised to power m. But it's very easy to check that you pick up the ever-changing term here, which doesn't go exponentially, but only as power in m. So now this matrix doesn't act multiplicative. It's not multiplicative on R squared. That was the essential thing. If we were able to multiply matrices, that's why we got exponentials, right? Because we would get something that adds up in exponent, but that doesn't work anymore. So if I write a matrix, JT, what I used to call stability matrix, e to the t of m, this is a thing that solves linear problems. If I just apply it on arbitrary two-dimensional point with two components, what I'll get is, from both of them, lambda here, e to the t lambda, u plus tv, I get a power law, something that's linear in t. So what this matrix does is it produces an exponential prefactor kind that we like when we are studying in linear problem exponential growth. But then it shears the first component, it just kind of stretches it out. You can do some gymnastics and put it upstairs as a log of t, so exponent is e to the log of t, if that makes you happy. But that's big trouble. On the other hand, it's quite common and you should remember it. Remember that you might run into the Hermitian matrices for subsets of matrices. We are guaranteed not to get that. So that's why you haven't seen it yet. But in your real life, you might see it. So what is the lesson? Even if you're looking just as simple as possible, matrices 2 by 2, not 100,000 times 100,000, there is no guarantee that they can be brought to diagonal form. The best you can do generically is to bring them to Jordan normal form, which has our usual eigenvalues on the diagonal, but if they're repeating eigenvalues, then there can be a diagonal of ones above them. And in this form, we lose the multiplicative nature of these matrices that brought us, exponentials of matrices as we studied evolution of time. we find out that on subblocks where I have degenerate eigenvalues and ones above them, I get power law behaviors, not exponential growth or exponential shrinkage as I do for diagonalizable matrices. It's not some weird peculiarities because in problems other than quantum mechanics and some parts of classical mechanics, you'll routinely run into this problem. For example, in fluid dynamics, it might happen. We are done with matrices. Next week, we will apply our wisdom to solve some springy, spring matrix problems or chemistry or whatever.